we're going to cover study on the damping electron. At the moment, let's focus that there is not any other devices upon the mass and spring system. Okay, so the single degree freedom is simply tell you that the capability of the system or the behavior of the system oscillating or vibrating, for example. So single degree freedom meaning that you have the one amplitude, you will have one displacement, you will have one natural frequency, and you will have one mode shape. So these are the model parameter, MODAL, model parameter, in way that you are presenting the vibration problems. Yeah. Okay. Let's go to next one. This one I've been talking earlier just now about the mechanical vibration, about 1 degree of freedom, the other one 2 degree of freedom. So this is 1 degree of freedom. We are going to cover free undamped today works and the free damped. This one, yeah, free undamped today, inshallah. The free undamped, the coming week, the coming lecture. Then you have forced damped. So if you have free here, free undamped, or even free damped, there is no external forces. But late of the lecture, we're going to have force here, meaning that you put something on the system. For example, yeah, you have a machine and the machine is unbalanced. So you are basically creating the unbalanced force to the system. So we call it force damped vibration. Or you put a point force to the system. In harmonic, of course, we call it also damped harmonic excitation to the system. It's still damped here, meaning that even though you put force on the system, there's still what a devices to absorb energy. Okay, for example, you're driving a vehicle, you are in your car, for example. So the seat, yeah, is acting as a damping, damping devices to absorb energy. When you hit a hump, for example, you will not be excited so much because most of the excitation is absorbed by the tire and also absorber, and before reaching to you, it's also seats. So there are many type of material absorbing energy. We call it a dampens. And when you're talking about 1 degree of freedom, as I mentioned earlier, you are talking about only one single behavior. Okay, typically in general work, yeah, when you have a one mass, you will have 1 degree of freedom. We have two masses, you have 2 degree of freedom. We have three masses, you have 3 degree of freedom. When you have n mass, for example, n, yeah, it also n degree of freedom. We call it multi-degree of freedom. We are going to look at that one later on. In the introduction of multi-degree freedom. If you're very keen to know more about this topic, you have to join me back in the later year of your study in option subject called mechanical vibration. The code is SEMM4213. That course will cover the whole thing, ranging from a simple vibration phenomena to the very complex vibration phenomena. And it is not only that, we're going to use tool here to make a comparison with the calculative or the calculating result to the to the computer simulation, and toward that leading to experimental, inshallah. Yeah. Okay, when you're the next part of the topic will be covered on 2 degree freedom. 2 degree freedom, still talking the same thing, free and damped and force and damped. There's not damped here because when you put damped here, you have many parameters. So the equation very long and very complex. So we try to avoid, the long the vibration phenomena in detail, because that one will be covered in your option course subject later on. Yeah. So you covered only 2 here, free and damped, also force and damped. Okay. This is the vibration. Scientifically can be defined as an emotion that repeats itself after interval of time. It keeps repeating. It is not static. Yeah, it keeps repeating. If you look at here, this one is vibrating, isn't it? So look at here. On the top right here is the vibration, is vibrating. Okay, in the engineering definition, deal with the relationship between forces and oscillatory motion or mechanical system. This one in the engineering definition. Scientific definition is so general. Yeah, you can turn to page 241 to cover the more information in your books. Yeah. This is another definition, perhaps, or into the introduction, what is the vibration all about. So ones will tell you, can define by a cyclic or oscillating motion. Doesn't matter you're talking about machine, you're talking about pendulum, or simple thing. Of course, yeah, in class here, we are going to talk only a system where you have a spring mass system, you have pendulum system, then you have the rotor and this. But in the actual phenomena, you have the, for example, yeah, coming from the lead machine, coming from the forging machine, so on and so forth. The actual, even about building is also part of the vibration, problems. Yeah. And we are going to cover the linear and also angular motion. As you all know, the linear will be, the straight line motion, x and y, axis, and the angular will be a part of that is basically pendulum representing the angular, and also shaft and also rotor. Okay, this is a very simple, animation to tell us about what is vibration all about. You know that some vibration, some motion can be, can be calculated. Some cannot be calculated. The calculating phenomena we call simple harmonic motion. The one that we cannot calculate, we call a random vibration. We are not going to talk about random vibration because it's very, very difficult for us to cover the whole thing. We are going to cover only the introduction to the vibration worlds. Yeah. Look at here, you have a mass, you have spring, and it will be keep oscillating and oscillating. This is due to the what equilibrium condition, where talking about, remember your first law, Newton's law stated, it stated that the particle will be remain what stationary until one force what remove or perhaps leave the mass, isn't it? Or perhaps they are, in other words, yeah, for example, a particle will remain in motion until one force will stop the motion, isn't it? So this one has spring and mass, it will be keep oscillating and oscillating and oscillating until you stop it. Or perhaps with the period of time, for example, couple hours, due to the energy will be dissipated, lack of energy, isn't it? Energy becomes smaller and smaller and smaller, then it won't stop by its own, isn't it? Yeah. Talking about the world here, for example, our world is keep oscillating, isn't it? Or keep turning or rotating in own axis. The minute the world or the earth will stop in the day of doom, isn't it? Or the day of Qiyamah, yeah? Okay, this is the simple harmonic equation y equal to a sine omega t, because it be oscillating at y direction. If you oscillating at x direction, for example, it becoming x here, x is equal to a sine omega t. This omega representing the way it be oscillating with a certain frequency. With this one is omega, it's not w, yeah. This one is omega, we call the frequency, yeah. The unit of frequency, you have two units, one with radian per second, the other one in hertz. Some call omega, can also be in the form of f in the hertz, this one in radian per second. Okay, that is one. The other one, this is the thing that you have here in class, for example, but the actual thing when you work like you work as an engineer, you need to know how much you know deflection of a beam, for example, when injected by the force. Typically you have a bridge, for example, and you have a traffic here, so the bridge will be keep oscillating, isn't it, or deflecting, isn't it? So deflection will be up and down, up and down. So the more traffic will be crossed over, so the more frequent will be the deflection of the beam of the road, for example, or the bridge, for example. So this is the actual phenomena when you're talking about vibration. But in class, we are going to do that representing by a mass and spring representations. Yeah? And not only that, we also have this one. This is pendulum. This one, a lazy pendulum, is oscillating a very very slow. In terms of the actual phenomena, for example, yeah, only sound will tell you that the drum has been hit, isn't it, or beat. Or perhaps you put peanut here, isn't it? You can put your peanut here on the drum, you hit the drum, then you see the peanut will be dancing, correct? So it tells you that okay, the drum will be hit or beat. But in the engineering perspective, you can also what you call it simulate the drum into that one. It will keep what? It will keep this one is it will be keep oscillating over a period of time. When you stop hitting, it will also stop here. This is very interesting topics. Yeah, this one, yeah, you have so many modes here. the easiest one is mode 1 up to mode 21 or mode n, for example. So it depending on how much information you want to collect from the drum. The reason is why you need this one, yeah, because you want to design the drum. Correct. You want to design the drum so that when you hit and hit, it will not what? It will not break off, fall. Oh, sorry, fails. Or perhaps the cover or the this one, yeah, or the what you call it, the casing of the drum will not break, for example. Okay, so many information regarding all the vibration signals here. This is what you call vibration spectrum. The engineering perspective in the real life of the engineer, yeah, you need to know this one. How much the beam will be deflected X and Y, for example. This one is deflection on Y, this one will be deflection on Y also, but you have two nodes here. One will be at the middle, the other one will be at the peak tips. This one only one at the tip here. Okay, so the more mode you go, so the more deflection on the beam. This is what you call I beam with one fixed end or fixed end. Yeah. This one in y-axis, you can tell this on one axis. You can also have to look for x-axis, swaying left and right, left and right. So as engineer, you need to know this one before you do anything, yeah, because you want to ensure that there is no resonance occurring on the system. The minute resonance occurs to the system, it will make the system lead to failures. What is a resonance? Resonance is basically when the natural frequency of the system of this one or the beam will be coincide with the forces that injected to the system. A very good exercise if you have you know you put you have a dashboard on in your car, yeah, you have a dashboard, you put something on your dashboard, for example tissue box or whatever, your watch, for example, you put on the dashboard, then you run on highway. Well, as you reach a certain speed, yeah, you find that the dashboard tend to dancing or to move or to rattling, isn't it? It will drop then, isn't it? Why? The reason why? Because resonance occurring. What is the resonance? The resonance basic, the speed of the vehicle is coincide with the speed of dashboard. So that is why it will keep now what you call it, uh, 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 you know, uh, amplify the certain huge vibration amplitudes. This one is only to that, yeah, it's only not only swaying left and right and also up and down here, but it can also twist it. This one is more complex. Twisted is the most dangerous phenomena on structure. When you have a torsional here, this is not there will be no topic in our in your no course, yeah. If you want to look this one further, you need to join me back, inshallah, in the later year of your study in mechanical vibration course, yeah. And this is done by animation or perhaps in computer, because you can look, yeah, the color, what do you call it, contour, telling you the red, blue, green, so on and so forth. The red will tell you the more no the more deflected to the system. Okay, this is another one representing in terms of vibration in our topics. Now we're going to talk about mass and spring here oscillating. We are going to talk about pendulum here, whether you're talking about the very hardworking pendulum or the lazy pendulum, doesn't matter. And we're going to talk a bit about shock absorber. This one, shock absorber, is basically applied to the vehicles or car or motorcycles. Yeah, you can look at this one. You can observe this one in your car. So our aims now is basically to define what be the natural frequency of the system. Okay, so let's go move or let's move to the amplitude of vibration. The amplitude vibration tell us that how much the mass will be oscillating, you do not know, or how big will be the amplitude. The amplitude vibration will tell you about the displacement, the velocity, and also acceleration. That is the unit. It can also representing millimeter, if you can see millimeter, or millimeter per second, or millimeter per second square, which is representing the displacement, velocity, and also acceleration. And these units, yeah, depending on what type of vibration you want to measure. For example, you're going to measure the building. So you want to measure the building, you cannot measure in meter. You cannot measure in millimeter. You cannot measure in acceleration. You need to measure in velocity. if you want to measure how much the engine will be vibrating, you have to measure in acceleration. So it depending on what type of work that you are dealing with. Okay, if you want to measure the whirling of shaft, WHIRLING, whirling of shaft, so you need to measure by using displacement. So you can use this one. You can check what type of units to be used in doing the vibration measurement by looking at the ESDU. ESDU will be the engineering system data units. Sort of handbooks. You can find them in library, or you can just type in the Google. You find the ESDU. Inshallah, I'll be presenting the ESDU to you. This is another one just to share with you what is the free vibration, undammed vibration, and damped vibration. You can read on your own. The free vibration, as I mentioned earlier, there is no external forces. The system will keep oscillating and vibrating in own sense. Typically, you're talking about mass and spring, it will be keep oscillating here. If you're talking about a pendulum, for example, it will keep oscillating also upon insert. There is no external forces. But before that, before you keep oscillating, you need to give motion or what called displacement, then it will be move. Otherwise you cannot oscillating. That is the proven of first law of Newton's. Yeah. Okay, this one just to tell you that you have the black one, the green and one, and the blue one, which have the same K, the same M, and finally when you let it go, first you display, then you let it go. You will go with delaying time one after another. You found that the amplitude is basically the same, even though it be delaying a bit. The black one will go first, for example, yeah. But you found that the amplitude will become the same, -2 and also 2 here. That is the amplitude, yeah. The undamped vibration, meaning that there's no external forces. The undamped meaning that there's no external devices to put on the system, so it will be keep repeating the oscillation until it's stopped by its own. So this one, it remain constant with time. For example, if you put a pendulum, for example, you get the pendulum swinging, then you let it go a couple of hours, for example, it will stop by its own. The damped vibration here is basically when you put something on the system and the device, or perhaps the whatever you put on the system, will be what absorbing the energy. And it be absorbing energy, it basically what diminish or perhaps reduce the vibration amplitude. It becomes smaller and smaller and smaller, then will stop. Comparing to the free vibration. This one you have to put additional parameter or additional device on the system or to the system. Look at here. Look at the first one, top left. This one, yeah, as I mentioned just now, you have a 3 mass with 3 different color of spring. Then it will be keep oscillating and oscillating with the same amplitude. And when you have this one down, right down, you have the damped springs mass system. Look at here. Green and blue, isn't it? A green and red. Look at here, this is the spring. Then you displace the spring and mass, then you let it go, it will keep oscillating, but the amplitude becomes smaller and smaller, then it diminishes, isn't it? Look at here, this one, there is no reduction of energy, so the amplitude will keep remain constant. This one, the amplitude becomes smaller and smaller, then it will diminish and become zero and stop by itself. The reason is why, because you damp the system. Okay, that is the introduction between damped system, undamped system, free, and also simple harmonic motion. Everyone here, even damped and not damped here, it will be representing to us the simple harmonic motion that you can calculate. You can calculate the area under the curve. You can also calculate the equation, perhaps. Yeah, you know the equation, then you know what will be the amplitudes. Our aims now is to look at the amplitude, for example. Yeah. This one, as I mentioned earlier, just now. Okay, this one is what is the degree of freedom. Just now is what vibration, free, force, and also damped and undamped. This one is talking about degree of freedom. The simplest one is what you have here, mass and spring. You have M1, K1. This one is X1. X1 be the tendency, the behavior of the M1 be oscillating. So if you displace this one, you bring it down, you hold a bit, then you let it go, it be keep oscillating. Correct, isn't it? Then we call what? We call number of variable required to describe the motion. So you have only one X because you have only one M. But when you come to 2M here, you have M1, X1, M2, X2. You have also K1 and K2 here. So if you, for example, yeah, you displace the M1, for example, this M2, we do not know where will be the behavior. This one be, you displace a bit with X1, then it will be oscillating. So the way we oscillating cannot be defined until you do calculation. This one is so easy. It can easily tell you that it will be performing simple motion will give you sine or cosine curve. This one you can't tell you. Some will give sine, some will give you cosine, depending on the animation or perhaps the oscillation of the system of these masses of the body. The simplest way to know that whether it belongs to a number of degree is to tell or to check on mass and also x. If you're one mass and one x, you call it 1 degree of freedom. If you have 2m and 2x, you have 2 degree of freedom. If you have 10m and 10n, it will be 10 degree of freedom. So to tell you, the simplest way to tell you whether it belongs to degree of freedom, just to check mass and also this one, yeah, the displacement. The x1 and x2 is the displacement. This one is 1 degree of freedom. This is our concern. Our topic will be covered by spring and mass. This one is torsional. We are going to talk a bit about the shaft and disc. And this one is a simple pendulum. And this one is the combination between the master spring and also pendulum, which is not in our topics. It is in the syllabus, but not in our topic. Okay, so we are going to cover this one, but more work on spring and mass and also simple pendulum. This one only no, only introduction or overview of the shaft and disc. This will be covered inshallah in the in the option course subject later on. Yeah. This one just to tell you that whether it belong to 2 degree of freedom. Look at here. You have two masses and two x, isn't it? X1 and x2. So it basically 2 degree of freedom. Look at the other one. You have as shaft here. You have this one and also this two here. So it basically coming for 2 degree of freedom. And this one will be angular motion. This one will be linear motion. This one same thing. This one in x direction. This one in y direction. But this one be the combination between the spring and also the pendulum, which is not in your topics. You hold on the class here. I'm going to plug in my computer. I'm running out of battery. Hold on, please. Okay, thank you. So are you still with me, class? So how many of you today? 48 of you. Are you still with me, class?
Yes, Dr.
Thank you, Lee. Yeah, thank you, Lee. So again, yeah, when you have number of degree freedom, so if you're talking about 1 degree freedom, you only have x1 and you have only omega 1. Can you see my cursor here? I show you omega 1 is x1. So x1 here is basically the amplitude of vibration. The omega 1 here is basically the natural frequency. When you have 2 degree freedom, you have what? X1 and X2. This one is not X1 and X1, yeah? This one is X2. Let me correct this one. I think yours is correct. X2 and X2. X1 and X2. The other one, leading to omega 1 and omega 2. So this one is simply tell you that you are talking about 2 degree freedom. What if when you have 3 degree freedom? You will have x1, x2, and x3. You also have the omega 1, omega 2, and omega 3. So the more omega you have, the more x you have, the more complex will be the system. But remember, as the more complex system, you have the more information to the system to overcome or to minimize the vibration on the system. Yeah. Okay, this one, the 1 degree freedom, again, come back to 1 degree freedom. This is our concern today. Look at here the position. Look at the most important thing, look at here, the motion and also the restoring force. Okay, the motion will be, excuse me, the motion will be toward my right, isn't it? But look at the restoring force is always again the motion. Or perhaps I can tell you the restoring force is basically kx. Here, this one, F equal to negative k. This negative will tell you that this one will be acting opposite direction. Okay, so when you define the boundary condition later on, you know, you give this one, for example, toward your right, so you have the kx toward left. So this is the important of telling you about the negative and in the animation here. Okay, any question up to here? Any question? Don't keep
No,
this.
doctor. No, doctor.
Okay, thank you, Kyo. Yeah, thank you, Ko. Look at here. This is when you have 2 degree freedom. Look at here. You found they had two M here, M1 perhaps, or M2 perhaps, K1, K2, K3, and you found that M1 equal to M2 equal to M, K1 equal to K2, K2, Km. So you look at all the stiffness are the same and all the mass will be the same. Look at here. So first, this one, yeah, look at my cursor here. First, you found that both red and blue running or moving at the same pace or the same direction, correct? And you have the overlapping, you know, this one curve, or what you call it, the displacement profile. Look at the second one. The second one now, the blue and the red will be what? Meet and we call it in phase, out phase, or meet together and repel. Isn't it? Or in phase, out phase. In phase mean that it coming towards together, and out phase mean that will be what, it will be displaced together. No, dispersed together. So look at the amplitude. One representing sine, the other one representing cos. And these two amplitudes basically having the same amplitudes or same magnitudes. Look at this, the third one. The third one, you cannot tell easily that both are running, toward or backward on the system. One will be running faster than the other, and you look at the graph presented here. So the amplitude keep fluctuating, isn't it? So this one is what we call random variation. Very difficult to define this one. This one is easy because you know that both are coming together and also apart, separated together. Our concern here, this one only, number one and number two. This one is not our concern at the moment. Yeah. You found this one. Yeah, the amplitude become the same because the k, the m is not identical. If you found that the m1 is not equal to m2, for example, then you found that one will be running faster than the other. That was the third one. This one again, to share with you what it is simple harmonic motion, because this one presenting simple harmonic motion. Okay, this is the simple harmonic motion. This is very important to know how the simple harmonic motion works. For example, yeah, this one will be the x. Look at the x1, the x, the red one, the red will be x, will be what? Will be the x direction. So you have x equal to r sine theta. R will be the radius of this one, link. And the other hand, you have the blue one here. The blue one representing the x and y here. Well, sorry, the red is y, the blue is x. So this one just to tell you that the amplitude of vibration, whether it belongs to the horizontal or vertical, it doesn't matter basically. What does matter now? Whether it is presenting simple harmonic motion or not. And on the other hand, you have this one, only a single one. It's easy for you to define, isn't it? Single one is easy. But when you have two here, a bit difficult. When you have three, more difficult. Even though it's creating the same, amplitudes. This one just to share with you, class, how is the how is the oh, how is this generation of simple harmonic motion. You have mass and spring here. Look at here, mass and spring on your right. Mass and spring, then you put a pen here, then you run a paper. Then it will creating or constructing or drawing the simple harmonic motion. Like what you have here. This one is the position of the mass when it run simple harmonic motion. From this one, yeah, negative A simply means the ultimate lowest. The positive A will tell you the ultimate highest. And between this one, we call the extreme extreme position at top, extreme position at bottom. And between A plus and A minus, we call the amplitude of vibrations. This is the actual one. Look at here. So this is the actual one, the pendulum. Then look at how far it goes. It go from 20 to 30, isn't it? 20 to 30. So you also have 20 here and move here. This one, look at here, the creation. You done this one in year 1, if I'm not mistaken. Yeah. Many years ago, I also one of the lecturer, conducting a year 1 course called I forgot about the course. Yeah. I forgot the course. What, uh, Introduction to Mechanical Engineering, isn't it? Okay, never mind. Put it here. This is another one. This one is the pendulum. This one is the spring here. So our aims now is basically to look at what? To look at what I call it omega n. Omega n is the natural frequency of the system. Doesn't matter what system you are dealing with. Yeah. This one just to recapture back the thing that we have earlier. This one is the again to tell you, how it works. Typically on simple harmonic motion. Look at here. When you have the equation xt, t meaning that x will be the amplitude version, t meaning that with what respect to time, isn't it? Equal to a cos omega t minus this one is psi. Yeah? Look at here. Psi is basically when negative because it will be beyond, or sorry, it will be below the origin. You have plus here, it will be at top. If this first curve or first graph will be at top, it will be plus psi here. So it depends. Sometime here it will be before that it's also negative. As long as the below the origin it become negative. Is at the top origin become positive. What is our concern here? This one, it doesn't matter, yeah, because this one very nice because it start at 0. Look at the 0. When you not start 0, so you have another one, omega t minus psi minus something to tell you where it will be starting point. So this one, the moment, let's start with 0 here. This one is to to consider our omega n. Omega is the natural frequency. This one is k by m. We're going to prove how this k by m is suddenly become an equation. We're going to prove later on by using simple harmonic motion equation. Yeah. This one is the what you call it, definition of natural frequency, and what is the significance of having natural frequency. You can read on your own. Yeah, the general one will tell you that it is the frequency at which elastic object naturally tend to vibrate. For example, yeah, you have a longer ruler, you put on the table, then you let it go to the ruler, project the ruler, acting like the what do you call it, the simply supported. Then you hold at one point, then you display it at the tip of the ruler, and the ruler will be vibrating. So you let it go, you're vibrating and owns 10 cent, meaning that if the ruler you put lump mass at the tip, so it will be vibrating quite a while before it stops. So that's why I say that elastic object, it must be elastic object, naturally tend to vibrate. Naturally tend to vibrate, it will vibrating by its own weight. This one is the scientifically definition. In mechanical, for example, is basically a structure can possess many natural frequency, as I mentioned earlier, mode 1, mode 2, mode 3, isn't it? So the lowest one is called fundamental resonant frequency. It's omega n1. This one again, you can read this one in your book. I put one special topic in your book talking about the natural frequency. So the importance of natural frequency. This one, as I mentioned earlier, just now is a ruler. This is not a ruler. Something like this one. You put this one, then you displace. It will move like whatever you have on the right, right figure. Huh? Or it can also be in the form of spring and mass, and we call this one equivalent. Equivalent simply mean that you have the actual one. Before that, you have this one. This one. It tend to be this one, the actual thing, and it can also be presented by K and M. Then we are going to look for what is the K representing the flexibility of the rod and what will be the M representing this ball. We will look that one later on. Yeah, this one is the pendulum. This is another one. Yeah, look at here. I suppose to have this one animation, but very unfortunate. I can't animate the system. I'm sorry about that. Yeah, just look at here. Look at your class. You have FN 1.4, 1.8, 2.6, 3.9. Can you see that in your notes? Hello? Or can you see in the screen?
Yes, we can see
Look at
it.
here, zero, yeah? Zero. This one, when you calculate it, you know this one at 1.4, 1.8, so on and so forth. This one, zero, mean that you stop the machine. This is the machine. So the machine will what? Move backward, forward, backward, forward. Okay, then you pull, and then you stop the machine. When when you start the machine, it will push backward, backward, forward, like the plunger here, like the piston here, backward, forward, back, forward. So you found that at 3.9, this one, the first close to the control panel will be displaced, isn't it? Or vibrating. This one is vibrating. While at the moment, the number two, number three, and number four will remain stationary. Then you keep speed, you increase the speed at 2.6. So the second will be vibrating, but not 1, 3, and 4. It will remain stationary. Keep doing that, the same thing, until you reaching 1.4. The same thing, the first three will not moving, and 1.8, this one, 1, 2, and 4, so not moving. So to prove this one, I got another animation, which more interesting. Before that, you know that when you have a machine, yeah, look at it, this one representing a machine. For example, the machine itself, or the engine for itself, you have so many compartment, or sorry, so many component, right? Beginning from the gear, shaft, bearing, piston, what else? Connecting, so on and so forth, even casing. So all the component will having what? Different natural frequency. Likewise, what you have this one, only four component. So that is why if you have so many information, you know that which no which omega n representing which component. It's easy for you to make the maintenance when things fails. Yeah, look at this one. Uh, Look at this guy, and this is not me. Yeah, and not my colleague also. I pick up this one in the Wikipedia. Look at here. This guy will want you have a 1, 2, 3. Like what you have this one, exactly this one. You have the you have the stiff rod, and you have a ball here with mass, of course. Then with different color coding. Then so this one you move. So at certain value, at certain speed, only one one rod will be oscillating. For example, this one of course, this one is steeper, this one is not very stiff, isn't it? This one is flexible, this one is very stiff. You found that the flexible one is, well, it will be vibrating much compared to the stiffer one. That is why at the end of the day, you know that failures come when there is deflection more compared to others. Okay. Of course, this one is what we have here, and we look at the actual thing. Look at the actual thing. This is the actual thing, and you have this one. This one is the accelerometer. What the accelerometer? Accelerometer is to what? To measure the vibration level. This one vibration and x. This, sorry, at y. This one vibration and x. So x plus y, we call it this one. What? This one. Sorry, class. This one xy. This one is x. This x plus y, we call this one elliptical. So the elliptical is basically the actual vibration phenomena in engineering perspective. Yeah. But the thing that we are going to look in laboratory, we are going to measure X, we're going to measure Y, for example. Then you add up together, it become elliptical. This is the combination of these two axes. Okay. Of course, yeah, when you do measurement, you cannot measure one X and Y. No, you have a special device to measure this one, what you call as triaxial vibration measurement. Is this triaxial? This one only one axial for X, for Y. This one only one axial for X. But in our work here, in our theory here, we're going to measure one after another. Remember when we do the gyroscopic, we measure the motion one after another. First turn to left, first turn to left, then no climbing. But at the actual thing, turning and climbing also occurring at the same time. Likewise, this one, yeah, X and Y occur at the same time. We call ellipticals. Okay, this is another one. Just to share with you. You know, when the vibration occurs on the system, look at the position here. This one will be everything quite well. Then will be overshooting, and will creating severe vibration. So at that time, you need to do something about it. You need to put damping, so on and so forth. Of course, before you do anything, you have to measure the thing. You have to measure the vibration level. To measure the vibration level, you need to know the theory. This is the thing that you're going to look for later on. Yeah. It is not only that, you also have this one. This is the what we call the you know, only one displacement on Y, for example, represented by simple harmonic motion. This one, when you have the misalignment, look at this one. The drum will be misalignment. This is the rotor, yeah, misalignment. And when it's in misalignment, also creating whirling of shaft. This is the shaft, whirling and shaft. You come to the this one is the green and the red. This one is what we call as this one, yeah, called as universal joint, and it will fail the universal joint. And you have to avoid this one. How to avoid? We are going to look at that one later on. Yeah. I have this one. Look at this is the pump, yeah, centrifugal pump. This is the motor attached to the shaft or the thumb by the coupling here. And you know that the pump will be, you know, this is the water, of course, pump in or pump out here. Discharge could be at the top and the bottom, doesn't matter. So what does matter that you get this one, look at the pipe here, it will be what? It will be vibrating, isn't it? Vibrating upon times. So this one is very dangerous in respect with failures. It lead to failures. So in engineering perspective, what we're going to do next is to what? To avoid this one, or perhaps to minimize the vibration level, to put something here at here, this one, what we call as isolation. ISOLATIN, isolation. It's a device or a material to absorb energy. Sorry, yes, to absorb vibration energy. This one is another one. Look at the yellow dot here. This one is still okay because it's rotating in the same manner, and this one is not okay because it is rotating, rocking here. This one is cylindrical motion. It's easy to overcome. This one is very difficult to come because it will representing the rocking motion with dynamic unbalance. This is why we study vibrations. I think you can read, you know, on your own. Basically, the most thing is to avoid failures, or at least to minimize failures. If you cannot avoid, you minimize the failures. Mm. This is the source coming from the vibration, right beginning from the pumps and so forth. And also this one, if you have a system with you have the input and also output, you have the tendency of here gear, tendency of alignment to be bend of shaft. You have the looseness of the motor. You have the unbalanced parameter in your general bearings. Yeah. This is the actuals. One of my research, I think a couple of years ago, I basically look at the tendency of a system in bearing failures. This is another one. And first, this the actual one. This one is representation. Yes, representation of the actual thing. Then you come to laboratory work to basically define what will be the thing that you measured on site. Okay, last but not least, we get to the measurement. This measurement, even though you found that the system, as I mentioned earlier, yeah, it will be tendency to rotate or to have it elliptical. You need to measure one after another. Here in class, we are going to measure either in X or in Y, depending on where will be the maximum level of vibration amplitudes. Yeah, this is the how it works. From the source, this is what we call source. Then you have the analyzer. We collect analyzer, then you're going to look for the spectrum. Then you know how much will be the vibration level to overcome. Toward that, you can also calculating the vibration level. The calculation will be, you know, doing in laboratory, and we're going to look that one. And the spectrums, yeah, looking the spectrum is expecting like this one. This is like, you know, when you hit something, the drum they will be keep spike here, or you can put you have a stroboscope, put your stroboscope on your heart, then you run a bit, you run faster, you run slower, then you know that your beat will be keep spiking and spiking. Then you slow down, you sit still, your heartbeat will be remain as this one, very nice curve. This one you can read on your own. I'm going to pick up only the one here. Vibration can lead to excessive diffraction failures, and this one, to reduce vibration, we need to proper design and machine mounting. The rest not in your syllabus. Yeah, only two, this one, first and two. Okay, that is all about the overview why we study vibration. So the next one we're going to do is the calculation of vibration amplitude and also vibration, what do you call it, oscillation. This one, okay, we are going to look for free unknown vibration, mass and spring system, pendulum, and also this and rotor and this system. The first one, this is the most important thing before we do the next one. So in simple harmonic motion, as I shown you earlier, you have three different equation. One tells you about the horizontal x double dot plus omega 2x. How you generate this one is basically, if I can share with you how the generation of the equation is basically coming from this one. Yeah, pick up one equation. If I can write something here, I'm going to stop. I'm going to stop this one. I'm going to stop this one. I'm going to share with you 1 minute, yeah, class. I'm going to pick up my file, and the file will be the empty one. So I'm going to pick up this one. Okay, do you have the blank screen with you, class? Do you have a blank screen with you?
No, Doctor, still no.
Okay, now, so I'm going to basically show you how this, when you stop this now, we stop and how we generate the equation of simple harmonic equation, and sometimes we call this one as where are you here, this one, we call this one as equation of motion of simple harmonic motion. You don't need to memorize the whole term of things. What you need to know is, you hold on a bit. I'm going to where are we here? Oh. Yep. What you have, plus I suddenly do you have this blank screen with you? Do you have blank screen with you? Yes, okay. I will share you this one, a blank screen. This one, okay, yeah. Okay, now I'm going to use, okay, let pick up one equation. Yeah, pick up from this equation. You have this one, for example. Pick up this one. Take one here. This one. Okay, so you have put it here in simple manner. Put it y up. Astaghfirullah. Y is equal to y sine omega t if say that r equal to y. Just now you have y equal to r sine omega t, isn't it? So put it y equal to y. So put it here y not, this is a big Y sine omega t. Okay, so differentiate. This is the equation, this is the equation, this one the amplitudes. Okay, so when you have dy naught by dt, you have what? You have omega y, big Y, this one cos omega t, correct? Or perhaps in other words, you can also put it y dot. On the other hand, if you have y double dot, y naught, yeah, y naught double dot, it basically presenting by dy naught square by dt square is equal to this one, negative omega to y sine omega. So this one, okay. But you know well that if you want to make this one to become your equation, what you have is y double dot, put it here, minus become plus omega square y sine omega t equal to 0. Correct? Isn't it? So you have two equations, two solutions here. The solution tell you that here, yeah, the solution will tell you that um, the solution will tell you that one will be the sine omega t cannot be 0. Why? If this one becomes 0, so there is no oscillation. So there is one when you simplify the equation, becoming y double dot plus omega square y equal to 0. The other solution will be sine omega t is not equal to 0. And this is what we call as differential equation of simple harmonic motion. Or in other way, it is not y here, it becomes x. It doesn't matter. Plus omega 2x equal to 0. Or perhaps in when you are dealing with angular, it becomes theta double dot plus omega square theta equal to 0. All these are known as simple harmonic motion, whether you're talking about linear or angular. So this is the thing that you have to understand about how this one. Okay. Then we move to this one. Let me. I need to. Share with you this. Stop sharing. Yeah, the animation because um, it's more, what do you call it? More presentable rather than the PDF. But when I want to write something, I go to the PDF. I'm sorry about keep changing the slides because that's the way, you know. I want you to stay awake in my class. Otherwise, you fall asleep because I've been talking here alone. Yeah, you also sit back at your 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 place. Yeah, when I keep changing the slide, then you make you a bit make you wake up a bit, isn't it? So now there were three different methods here to define the omega n. Remember that our mission is to define omega n. Remember that our mission is to define omega n. Omega n. What is omega n? Is natural frequency. So we're going to look for Newton's law, classical method. Some would call it classical method. We call it the energy method. We call it conservation of energy. This is the equation, and this equation is not new to you, and this is new to you. The first two is not new to you. The last one is new to you. The equivalent system method, or some call Lamb-Mesh system. If you go if you find in book, yeah, don't look for the equivalent system, but look for Lamb-Mesh system. LUMPED, Lamb-Mesh system. Okay. Don't go for the equivalent system. There's no equivalent in the books. Typically Lamb-Mesh system. So many books talking about Lamb-Mesh system. So what is Lamb-Mesh system? When come to the example, we dealing or talking or explaining details. At the moment now, let's us focus on this one, classical methods. Okay, classical method. Okay, this one. I'm going to share with you again. As I mentioned earlier, I'm going to stop sharing this one. I'm going to pick up my PowerPoint here. Sorry, it's not PowerPoint. I'm trying to pick up this one, yeah, PDF. So I'm going to share with you how we are going to generate this equation omega n. Oh, astaghfirullahaladzim. Supposed to be, sorry class, yeah. I'm going to go back to the because I need the animation. Yeah. Look at the animation. So our aims now is to tell you or to define why the mg equal to k delta. This one is static. First at rest, then you first look at the first one. The first one, spring, but there is no mass. When you put mass, it will deflected a bit by delta, and you know that mg equal to k delta. We're going to prove this one, mg equal to k delta. Then you, with mass and k, you displace. This one is static displacement, then you displace. This displacement that you pull down a bit, then you let it go. As you let it go, it keep oscillating upon what? Upon ultimate maximum and the ultimate minimum due to the width and also due to the stiffness of the spring. Okay, how this equation going to generate, I'm going to share with you now. Okay, now I'm going to stop sharing here. I'm going to open up the because when I keep in one slide, I think check on your book. Do you have this new screen here?
Yes,
Hello?
doctor.
Yes, thank you, Ang. Yeah, thank you for respond to my question, or I will like I'll keep asking you whether you receive or not the screenshots and so forth. Okay, now look at this. So this is the first one just now. There's no displacement because the spring will be at its own position, and you study this one at rest in dynamics at rest. Spring at rest, there is no deflection yet. Then you put mass here. Then we have this one delta. This delta we call it static displacement, isn't it? Then you displace you displace m, then you let it go. This one you let it go, you let it go. So it be oscillating and creating the simple harmonic motion. This one we call simple harmonic motion. So first our aim is to define the equation. So let's put this here, number 1, number 2, number 3. This one is number 1. K, put a mass delta. This is the free body diagram. Free body diagram. What you have is summation of F. Put it here. You want to put Y, put it Y is equal to MAY. We are not going to use AY now. We're going to put X dot or Y double dot. I'm going to put here F equal to MX double dot. Even though X representing by not by horizontal, I'm going to put X as SY, Y plane, doesn't matter. Doesn't matter as long as you know where is Y and X falls. So now, and equal to 0 because we are dealing with static. This one is static equilibrium. And saying that you need a boundary condition, isn't it? You need a boundary condition saying that, okay, anything that move or pointing downward is positive. So you have here, you will have negative K delta is equal to, or perhaps you can start a very simple equation where you found that it is basically minus by mg, sorry, plus mg equal to 0. Why plus? Because this one plus, because I'm putting this one pointing downward as positive, and this guy will be pointing downward. This one positive, this one is negative. Then you simplify the equation, it becoming mg equal to K delta 1 equation. And this call this one as static deflection equation. Okay, static deflection equation, this one. And very important, this one. How it is important, well, I will tell you later, not now at the moment. So now, the second part of the equation, that supposingly now, when you pull this one and it displace this one, isn't it? Displace D and let it go. So it be oscillating. So now, this one is number 2 and number 3. 2 and number 3, both. Okay, and still using the same equation, xx equal to mx double dot. Anything that pointing downward considering as positive. What you have here is you have negative K delta plus x. Why? Because the first thing just now is delta. Then you have another one oscillating. This one. This one add together. Okay. Then this one, what pointing downward, is plus mg equal to this one, the mx double. It's not very difficult, isn't it? Then you open up the bracket, or perhaps you bring in one equation. Yeah, you find mx double dot minus mg minus become plus k delta. This one, or perhaps in the very beginning, this one let do this one after another. Positive delta plus x. Open up the bracket equal to 0. So this is mx double dot minus mg plus this one I miss k. K delta plus kx equal to 0. Correct? But remember this one mg equal to k delta. So you put it together here, you come mx double dot minus by mg k delta plus by k delta again plus kx equal to 0. This one cancel automatically because there is no more static, static parameter in the dynamic oscillation. So you have mx double dot plus kx equal to 0. This one is known as equation of motion of spring mass system. Is that clear? Do you understand, class? Hello?
Yes, doctor.
Now, we are going to rearrange the equation. Remember just now what you have just now? You have x double dot plus omega n square x equal to 0, isn't it? What is called? It's called differential equation of motion of simple harmonic motion, isn't it? So we're going to equate this one. So equate, before equate, you have to rearrange the equation. Rearrange the equation. How do you arrange? This one, yeah? X double dot plus, bring the m, under k, yeah? M x equal to 0. So these two equations now look alike, isn't it? Correct or not? That equation look alike. Okay, so one solution by equating the equation of motion with differential equation of motion of simple harmonic motion. If supposingly I put it here, this one is A, this one is B, for example. So it's basically this one is differential equation motion is what is B. This one is A. You equate these two equations. So what you have here, you pick up the common one, the second term of the equation. So what you have, you can simplify this one. You have omega n square x is equal to k by mx equal to, sorry, isn't it? Then you simplify, cancel, lead to omega n square equal to k by m. Or can also be written as, omega n equal to k by m in radian per second. Okay, or you want to change this one to become frequency, for example, this one is omega n. F is always omega n by 2 pi is equal to 1 by 2 pi equal, k by m in the unit of hertz. Hertz is cycle per second. This is solution number 1. Any question? Any question? We're going to move for solution number 2. Solution number 2. Number 1 is by equating the equation motion with different equation of simple motion. Number 2 is by also equating with simple harmonic motion, with harmonic motion. With harmonic motion equation from what just now? From B. From B, from B. From B, you have x double dot plus k by mx equal to 0. This is the equation of motion. Some would call this one differential equation motion. Both are mean the same thing. Yeah, some call equation of motion, some call differential equation of motion. This one give you the same meaning. Are you still with me, class? I don't know whether you follow me or not. I don't know because you don't know basically. Yes, Nazifa. Thank you, Nazifa. Thank you, Lee. So now let harmonic motion. What does harmonic motion tell you just now? What? X equal to what? X sine omega t, isn't it? And you put another one, x dot is equal to omega x cos omega t. You put another one, x double dot equal to negative omega square x sine omega t. This is omega is equal to omega n. You can put this one omega, you can also put this one underneath subscript omega n. So then put it there, equation C. So you substitute C into B. Substitute C into B. What do you have? You will have, look at here, substitute this one. So you will have, okay, negative omega square x sine omega t plus k by m is a constant parameter. Your x is x sine omega n t equal to 0. I don't want to put n here because I don't want to make you confused. I put it omega. Then you know that omega is basically belong to omega n. Correct? Then you simplifying this one. You be getting what? You be getting negative omega square plus k by m. Put it in bracket. Factoring sine omega t. Sorry. Left x here. X sine omega t equal to 0. So the solution leave to you. Put it two solution. The solution S1 will give you what? X sine omega t is not equal to 0. We call it non-trivial equation. What is non-trivial equation? So if this one equal to 0, what does it mean? So there is no oscillatory. So it cannot be 0, isn't it? It cannot be 0. It must be what? Not equal to 0. It equal to 0, so there is no space, so there is omega and it become all 0. So what does that mean? So the spring will become static. The system will become in static. Yeah? The other solution will be you have omega negative, yeah, square plus k m equal to 0. So therefore, you take this one. So therefore, you have omega square equal to k by m, and will give you omega n equal to k by radian per second. Same as before. Any question? Any question? Any question?
Doctor,
Yes.
what is the x actually? The because in the book is mentioned with the radius r.
Radius r. Which
I
one?
mean for the x sine theta t, omega t.
Uh-huh.
What is the x? Because in the book is mentioned that y equal to r sine omega t.
Oh, y. Okay, let me because it's not y equal to what does
R,
not you say?
r sine omega t.
Sine omega t. Okay, this one, yeah. The reason is why put it here. Oh, go back to the principle just now. Where are you? This one, yeah. So I'm saying this one, yeah. Look at here. This is the this is y, isn't it? So when this one reach to this one, so y equal to correct or not?
Yes, doctor.
When this one, this so because our aim is to look for y. So now y is equal to r sine theta. Or you can also put y equal to y because what is the age of the or the maximum level of the equation. Am I answering your equation?
Understand, doctor.
Okay. Okay, now come back to this one, yeah. Okay, we have another one. Remember, this one is by using using Newton's law. This one by using equating by equation. The other one I'm going to share with you is to use energy. In books, not the books give you the equation of energy is defined by d by dt ke plus pe equal to 0, isn't it? Yes or no? Or in my notes? Yes or no? Hello.
Yes, doctor.
So let's go back to the to dynamics. So what dynamics tell you? In energy topics, you have U is equal to delta T plus delta VE plus delta VG. Right, isn't it? So this is what you have done in dynamics. But if no external forces, U becoming 0. Correct or not? So now 0 equal to delta T plus delta VE plus delta VG. Okay, so if no gravitational T or energy, so delta Vg becoming 0, so this one becoming 0, isn't it? So you have only two. 0 is equal to delta T plus delta Ve, and this is what you are doing at that particular instant. You measure, you calculate at that particular instant. Meaning to say that there is no what? There is no time, no t included, no time included. But when you have a time here, so it will keep what? It will keep changing the value for delta t, isn't it? And delta VE. So delta t now is equal to Ke kinetic. Delta VE now is equal to PE, potential elastic energy. Yes or no? So then with respect to time, then you have PE plus KE equal to 0. Same thing or not? It's exactly the same what you learned in dynamics. The only now you have this one because with respect to time. With respect to time. Okay. When you understand this one, then we move to move here. Okay, now you have delta T PE plus KE equal to 0. So PE is basically what? PE is basically, what is your PE basically? The potential elastic energy. So what do you have for potential elastic energy for mass and spring? Anyone? Could anyone tell me what you have for potential elastic springs? Anyone? Potential elastic energy for spring. What do you have? Is half kx power. Am I correct or not? And you have Ke is equal to half m v square. There's no v here. We move v, sorry, change v to become x dot, where v equal to x dot. Then you take this one, put it in the equation. Put in the equation. So what you have is d by dt, PE will be half kx square plus ke will be half mx dot, this one square, sorry, square, equal to 0. Then you differentiate with respect to time, of course. So you have the power constant x dot plus the power constant x double dot equal to 0. Are you following me, class?
Yes, doctor.
Hello. So can cancel here, you can cancel here. Let me change the color so that you can differentiate it. So you have this one K X plus M X double dot X dot equal to 0. Then you have two solutions, remember? The solution will simply tell you that X dot will not equal to 0. What is the X dot? Is the velocity. And the velocity becomes 0, so there is no oscillation. There is no oscillation. Only have your X here. Isn't it? On displacement only. So you, as there is no as there is no oscillation, there is no motion, there is no omega n. Remember that. No motion, no motion, no oscillation, no omega n. Okay, no motion, no oscillation, no omega n. Okay, so what we need the omega n now, because our aim from the very beginning, we are going to look for omega n. So the other solution will simply tell you that your mx double dot plus kx equal to 0. This one is seen that we already done earlier, isn't it? So let's do this, the simplest one by equating with differential equation of motion of simple harmonic motion. How is it? We have x double dot plus omega square x equal to 0. Then you simplify x double dot plus k by m x equal to 0. So you pick up the second term, this one. So therefore, omega n equal to k by m, radian per second. Same as before. Any question? Any question?
No, Doctor.
Okay. Remember the three methods that we learned today. One is what you call Newton's law or classical method. Newton's law, or some would call classical methods. Basically, you are applying this equation. The other one we will study is energy method. Equation is d by dt, ke plus pe. The third one, this one is new to you. We call it what just now? What we call it? Astaghfirullahaladzim. What we call it? Equivalent methods. In book, they put it here as this one, L mass system or LAM mass system. Before I proceed with this LAM mass system, a new thing to you, I'm going to explain a bit. So it used in solving problem. Used in solving complex problems, complex. Used in solving complex problem to simple one. Right? So now tell me, what you have here is this one, simple or complex? This one, simple or complex? Simple. So we cannot use, we cannot use, it's no point of using this one. Complex mean complex. What does it complex? Complex means that you have this one is complex, yeah. This one is rod or bar or beam. You have spring. You have another spring. This is complex now. Is this one M? This one is K1. This one is K2. Then you have another one M. This one M1, this one is M2. This is complex now. Then only this one we can introduce the equivalent method or Lam-Mes system. Okay, at the moment now maintain as what you have here. There's no using of users of the Lam-Mes system. Okay, second system. I'm going to share with you now the second system, pendulum. Have you copied this one? Can I change to new slide? Hello?
Doctor.
Yes? Okay, thank you. So get this one. The pendulum. You can check on your note and you can also check on your books, yeah? So we are going to look at the same thing. Our aims now. What is our aim? Is to define omega. Is to define omega n. Is our aim. Let's say now we put another parameter to define. Instead of only omega n, we're going to look for Tn. Tn is basically 2 pi by omega n. What is T? T is the one? The vibration periodics. This one is periodics. Is it radian per second? Is this correct or not? The equation T is this one is second, yeah. So you have omega n radian per second. So if you multiply by second, so yes, correct, yeah. Now, how is it? This one. First, number one, use Newton's law. This one, yeah, Newton's law. As I mentioned earlier just now, when you deal with Newton's law, you must have one free body diagram, isn't it? So it's compulsory to create or to construct the free body diagram. So let us now move to the dependence now. So this is at rest, pendulum at rest. There is no oscillation. Here, omega n equal to 0, t equal to 0, x dot equal to 0, x double dot equal to 0, x also to equal to 0. Everything at 0. Here, then you have omega n. When you display this one, you displace and let it go. So it be oscillating. It will create oscillation. Angular. This one is angular motion. Okay, so you were oscillating from the extreme high to extreme low, so on and so forth. So this is the free body diagram now. So you pause a bit because you want to create, you want to analyze the free body diagram. You have to pause a bit. You pause a bit. So the creation of the component of force, mg sine theta. This one is mg. This one is mg cos theta. And this one also, you have this one. Remember, this one is f1 fn, isn't it? The fn. And this one be your ft. Remember, if you're doing this one, ft. This one is the tangential. This one is a normal. It's always pointing inward. Isn't it? So before we do this one, I also want you to know that what is the pendulum. So before we solve this problem, let us define what is pendulum. Okay, we go back to the figure because I don't want to, I don't want to keep drawing the pendulum because my drawing is not as good as what you have in your notes. Yeah, what is the pendulum? So now, look at here. The principle that you study in dynamics, they are saying that the free motion, yeah, or rigid body motion. So it seems that any motion doesn't matter whether it belong to you have a ball here or blob here, suspended or supported, or you can also have this one. This one is uniform. This one is uniform rod, or you don't have uniform rod. You have this one. As long as all this thing will be in vertical. Remember that in what vertical plane. Vertical plane, yeah, it's not x plane, vertical plane. When you have a vertical plane, of course you will have the mg, and it is what free motion. What the free motion? No restriction. There is no restriction. What is the restriction? This is the restriction. What is the restriction? This is the restriction. Okay, so if there is no restriction of k, for example, it is not only k, sometimes you have c. What the c is a damper or dashpot. So as long as there's no restriction, so it will be considered as pendulum. Remember that one, yeah? Vertical with mg, no restriction, free motion, pendulum. Doesn't matter how does it look like, whether it is supported or suspended, whether it is this one is uniform or not uniform, doesn't matter. Sometimes you will have this one, the L shape. It's also pendulum because it is in vertical plane. Is that clear? So we coming to this one, then we check, oh, this one is a pendulum. Then you move to the solution. Understand me or not? Yes, no, class.
Doctor, can you come again? I'm not quite understand.
Which one? The pendulum.
Yeah.
Okay, now again, yeah. This is very important because some problem it might be, ignore the pendulum. Sometimes you have to take into consideration of the pendulum. So now, so just remember the keyword of the pendulum is any mass. This one, any mass in vertical plane. Remember that vertical plane. Why vertical plane? You have the mg effects. Mg effect, the mass or the weight effects. Whether this one is supported, this one is suspended. Sorry, this one is suspended, this one is supported. Doesn't matter. Whether this one will be what? This one is uniform beam or not uniform beam. You have another mass here. Doesn't matter. It will be considered as pendulum. So as long as no restricted, what is no restriction? Meaning that no K, no C. This one. Later on you study about C. At the moment you know K only. This is K. So this one is restricted. Not restricted this one. All free, not restricted mean the free, what free motion. This one is not friction, it's controlled by K. Right? So this is not pendulum, this is not pendulum. This is yes, this is yes, this is yes. Okay? Clear? Now we move to one. As you look at here, very careful. Okay, this one is no restriction. There's no K attached to M, attached to the pendulum or the ball. So you can use the three different method. One will be Newton's law. Okay, Newton's law. The Newton's law is not very difficult. We try to use Newton's law. The simplest one. You have summation of M equal to I theta double dot. What you learn in dynamic, O about O, because this one is about O. What you learn in dynamic is I O alpha. What you learn in dynamic in very principle is not this one. You learn in dynamic basically from the general equation. You learn what? Summation of M equal to I alpha plus MA D. Remember? Then you have special topic on that. Is the what? What is the special topic? Rotating what? Rotating about fixed point. This is rotating about fixed point. You have this equation. Okay. Then you have the boundary condition. What is the boundary condition? Who decide? You have to decide on your own. I'm saying that okay, the boundary condition will be rotating that way will be considered as positive. So you will have from this one, you have the mg, negative mg sine theta multiplied by L, because we are talking about moment, correct? Is equal to I naught theta double dot. Okay, but what you need is this theta, small displacement, a couple of minutes, for a minute. This small displacement, this one theta approaching to 0. So when approaching to 0, what does it mean? That when theta approaching to 0, you will have what? Cos theta, cos 0 equal to 1. Sine 0 equal to 0. It simply means that sine theta equal to theta. Isn't it? So when this one in mathematics, in mathematics. So you take this one and put in equation. What you have is negative m. This one is sine theta become theta now L equal to I naught theta double dot. Okay. Then you know that this I naught is the mass moment initial is equal to what? Is equal to ml square. Where it come from? It coming from I naught equal to mk square. This k will be the radius of gyration is equal to L. Then you expand the equation, it becoming mg. This one is L by theta is equal to, this one is ml square theta double dots. We arrange the equation, it becoming m theta double dot. This one plus, bring it here, become mg astrology. Yeah, this one is supposed to be ml square theta double dot. It is correct. Plus mg L theta equal to 0. This is what we call as equation of motion of pendulum. Simplify, remember, you simplify theta double dot plus this one is mgn divided by m L square theta equal to 0. Cancel, 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 cancel. Then you will have, you leave you g by delta equal to 0. Then you have two methods. One will be one will be equate with differential equation of motion of simple harmonic motion. The other one with harmonic equation, harmonic equation. I'm going to use the first one. So therefore, from theta double dot plus omega n square theta equal to 0. What we have is that theta double dot plus is g by L theta equal to 0. Then you pick up the the equation related with the term, this one. You will have omega n is equal to g by L, or we have the omega n equal to g by radian per second. So now I'm going to let me have you a couple of minutes, 2 or 3 minutes. Look at here, where this been used. Where? For example, yeah, you have a crane here. Crane. I'm not good in drawing class. Sorry about that. You know what crane is? You know what crane is? This is crane. This is the structure. This one is crane carrying a I-beam. This one to build B-U-I-L-T, to build a bridge, B-I-D, bridge. Isn't it? So this crane will swinging this I-beam, correct? This one you can move that point. This one can move that point, rotate. Okay, let's say now on this one not move. This one omega equal to 0. This one only can move up and down, up and down. and it will be acting like pendulum. So you as engineer, you have to what? You have to ensure that the omega n of this crane is equal to G by L, where the G will be the gravitational value and the L will be the length of the cable. And it will not be coincident or coincide with the omega, this one, yeah, omega of this crane, omega crane. If this one be coincide, so it will fail. So if the omega n equal to omega crane, so it will fail. So that is why when you work as site engineer, you have to ensure that this L will remain constant, and the operator will not simply playing with the L. Because why? You want to keep this one constant. Okay, if this one keep playing with the L, so it will keep what? Changing the omega n. And the tendency the omega n will meet omega crane, it will fail. How it fail? This one will, the crane, this one will break. This one will, when this is what we call as resonance. Okay, I think we finish at pendulum. So when I meet again, I'm going to talk about pendulum. When we do energy, and also we be talking inshallah about the shaft and rotor. Any question, class?
Thank you, Doctor.
Any question? I really hope that you enjoy the lecture so that you can pick up all the of course the knowledge in class, and also to apply during the time when you come when you be engineer one day, inshallah. Okay, if there's no question, so thank you for being with me. Thank you for those who keep responding and participate in class, so that make the class lively, and really enjoy to to share knowledge with you guys, and hope that you enjoy, and all the best in your studies. So with that, I end my session with Assalamualaikum warahmatullahi wabarakatuh. Hope to see you again, inshallah, and stay healthy and stay safe, and have a nice day. Thank you.
Doctor.
Hey, Doctor.
Excuse me, Doctor.
Yes.
Because in the book is used that Rayleigh method, so is it same with the Lamb-Mesh method?
Yes. Lamb-Mesh is equal to equivalent methods. But
So
if you look equivalent method in other books, I mean in other book, not my book, yeah, in other book, you can't find the equivalent method. You have to look for Lamb-Mesh system.
Because just now I saw in the book is right that Rayleigh method, so I quite confused.
Okay, so in my book I all use equivalent method. In other book you call it Lamb-Mesh system. Basically these two are basically equals. Okay.
Thank you, Doctor.
Okay, thank you.